Hello everyone and welcome to Sky Scholar. Today our series on various star type resumes. In the next few videos I wish to outline how our current understanding of white dwarf stars evolved from the theory of gaseous stars. I will also present an alternative view for the formation of the white dwarf within the context of the liquid metallic hydrogen solar model. White dwarf stars are found in this region of the HR diagram. Since they occupy the bottom portion of the diagram, their luminosity is low. However, they are also located to the left of the figure, so their surface temperatures can be elevated. The combination of these two factors, along with known masses measured when a white dwarf like Sirius B is part of a binary system, have led the astronomers to conclude that white dwarfs are highly compressed objects with masses on the order of the Sun, but with radius on the order of the Earth. As we go through our analysis, the logic behind these conclusions will be examined, and we will reconsider the nature of these stars. White dwarfs constitute an extremely interesting star type, so let us begin our analysis. A few weeks ago, the main sequence of the stars was presented on this channel, and I highlighted that the photospheres of these stars share the lattice structure of our Sun's surface. This was followed by a video on star formation which emphasized that stars are likely to be formed in relatively cool molecular clouds through photon-emitting condensation reactions. In this context, stellar birth is likely to begin with the trihydrogen cation. With additional condensation reactions, this cation ends up forming small clusters before growing to ever larger ones. The presence of positive charges acts to stabilize the clusters against sublimation. Of course, as large clusters grow, their surroundings can become increasingly warm. This is because in an astrophysical setting, conduction cannot be used to transport heat out of the cluster. As a result, photon-emitting condensation reactions must be used to channel heat into the surrounding medium. You also recall that in this video, photon-emitting condensation reactions were used to dissipate heat during the synthesis of condensed hydrogen structures in the chromosphere. That is how the presence of chromospheric emission spectra were explained in the liquid metallic hydrogen solar model as outlined here. We will return to the idea of building a star from simple molecules through photon-emitting condensation reactions in future videos, as there is no viable alternative in an early universe. In the last video, I also demonstrated that ideal gases cannot undergo gravitational collapse because the collisions which they sustain are always elastic. In this video and several others, it was seen that the application of the virial theorem to ideal gases leads to a negative heat capacity, which is known to be false. Gases always possess a positive heat capacity and are never gravitationally bound. Hence, the virial theorem cannot be applied to such systems. I have repeatedly argued that gravitational collapse cannot take place in an ideal gas, and now here is an interesting quotation along these lines from another group of scientists. We cannot refrain but wonder about the opinion Eddington and Jeans would have had regarding these results within the perspective of their famous strong debate, and also that of other scientists who touched on this matter, whom we became aware of by reading the interesting survey of Robitaille. Finally, we wish to close our concluding remark with a thought as well as future work-provoking reflection. The important message that springs from the results we have presented in the preceding sections is loud and clear. Perfect gas and self-gravitation are incompatible concepts within the Newtonian scheme of gravity. These are the two Robitaille papers which are cited. The central point from this quotation is that the gravitational collapse of an ideal gas is impossible. As a result, there is no way to make a star from an ideal gas, as Eddington so strongly advanced in his classic text. Now, some will claim that general relativity might provide a solution to the problem with its space-time curvature. In fact, that is what these very authors suggest at the end of their paper. But the fact remains that the second law governs the behavior of gases, a point which is all too often ignored. Gases expand to fill the void. As a result, one cannot make a star from the collapse of an ideal gas, contrary to what has now been argued using Newtonian gravity and astrophysics for the last 150 years. The point I just made is important. The idea that the white dwarf was a highly compressed object was advanced by Eddington, then solidified by Subramanian Chandrasekhar. However, this concept rested in its entirety on gravitational collapse of an ideal gas from a Newtonian perspective. If gravitational collapse of an ideal gas is invalid, then one cannot make a white dwarf with the enormous densities that Eddington and Chandrasekhar envisioned. Furthermore, this also destroys any claim that massive stars at the end of their lives collapse into black holes. In order to better understand what has happened in astrophysics, let us return to the mass-luminosity equation advanced by Eddington, because it is through the formulation of this equation that stars became viewed as comprised of ideal gases. Now, it is an observational fact that the main sequence of the stars possess a mass-luminosity relation, as can be seen in this figure from Eddington's classic text. Massive stars have more luminosity. Yet despite this figure, Eddington had an extremely dangerous approach to the study of astrophysics. He would completely dispense of the idea that convection played an important role in the sun and replaced early thoughts along these lines with internal radiation, despite the fact that he had no evidence whatsoever for his position. Today, we know that the internal layers of the sun possess powerful convection currents and that the surface of the sun is characterized by differential rotation. So why did Eddington abandon convective processes? The answer is simple. He was searching for a means to prevent a gaseous star from collapsing upon itself. Eddington believed, contrary to what we have seen in the last video, that ideal gases could experience gravitational collapse. Nowhere in his work did he ever consider that collisions within an ideal gas are elastic. He would argue the following: we can imagine a physicist on a cloud-bound planet who has never heard tell of the stars calculating the ratio of radiation pressure to gas pressure for a series of globes of gas of various size. But unfortunately for Eddington, he could never prove that his stars possess either gas pressure or radiation pressure internally. He had protracted disagreements with Jeans about the nature of the stars. Eddington argued that the stars could be treated as ideal gases, while Jeans wanted liquids, as one can learn in this review. Yet neither Eddington nor Jeans ever considered that metallic hydrogen could act as a solar building block. Of course, Wigner and Huntington had proposed that metallic hydrogen could exist in 1935. By then, Jeans had abandoned his liquid stars, and Eddington had published his famous book, The Internal Constitution of the Stars, in 1926. It is important to remember that it was Eddington's treatment of the mass luminosity problem which made all the astronomers believe that stars could be treated as ideal gases. In Stars and Atoms, Eddington stated that the sun's material, in spite of being denser than water, really is a perfect gas. It sounds incredible, but it must be so. Not only that, Eddington would argue that because the atoms were essentially stripped of their electrons within a star, that they could actually behave as superperfect and more easily compressed than any other gas. He completely showed his detachment from objective reality when he wrote, "Being an astronomer, I naturally put the connections somewhat differently and regard the physical laboratory as a low-temperature station attached to the stars. In it, the laboratory conditions which should be counted as abnormal." In the end, Eddington would simply ignore much of laboratory physics, which is the very basis of physics as an experimental science. Jeans, in fact, considered Eddington's solution to the mass-luminosity relation as little more than a mathematical trick. He stated, "All of Eddington's theoretical investigations have been based on assumptions which are outside the laws of physics." He also argued against the application of the ideal gas law to the stars. We investigated the internal equilibrium of the stars on the supposition that they were masses of gravitating gas, in which the gas laws were obeyed throughout. The investigation was abandoned when it was found to lead to impossibly high values of atomic weights of the stellar atoms. This created a suspicion that the hypothesis on which it was based was unfounded, and that gas laws are not obeyed in stellar interiors. All of these quotations can be found in this paper. As to the relation between mass and luminosity, Stephen Crothers and I have never disputed the observational reality. However, we have analyzed Eddington's treatment of the mass-luminosity relation, and we object to this mathematical solution. We have discussed Eddington's solution in this paper, which can be consulted for further detail. For now, we can just focus on the salient aspects. First, we begin by presenting equations 83.4 and 84.6 taken from Eddington's classic text, which can be combined to produce this equation for an ideal gas star. In these equations, m is the mass of the star, m sub theta is the mass of the sun, g is the universal constant of gravitation, mu is the molecular weight of the gas, c is the speed of light, kappa sub naught is a constant of stellar opacity, and L is the luminosity. Beta is a constant which relates the total pressure P within the star to gas pressure as follows, where the total pressure is actually the sum of gas pressure and radiation pressure. The problem is that although these expressions appear correct on the surface, Eddington's equations are not a solution as they violate the laws of thermodynamics. In order to see why, let us write down Stefan's law for a black body. We know that this law is thermodynamically valid. It has been verified as true in numerous laboratories around the world. In this case, A is the surface area of the spherical object, epsilon is the emissivity, which is assumed to equal 1 for a black body, sigma is Stefan and Boltzmann's constant, and T is the temperature of the object of interest. Now we have two equations for luminosity. Let us assume, like the astronomers, that the stars can be treated as simple black bodies and equate the two. Now, since the area is equal to 4 pi r squared, let us divide everything by area, which simplifies to the following. Now we must determine the thermodynamic character of these expressions. Unfortunately, this is something that few people seem to understand, so I will deal with this case in detail. First, luminosity is not an extensive property, and neither is area, but both have the same thermodynamic character, since they are both homogeneous functions of degree 2/3. As a result, L divided by A results in an intensive property, so the far left side of this expression is intensive. Now on the far right, the two constants do not contribute to thermodynamic character, so we are left with temperature, which is intensive. Raising an intensive property to the fourth power does not change its character, so the far right side of the expression is also intensive. This must be true since temperature must always be intensive in thermodynamics. Otherwise, one cannot even speak of thermodynamics. Now have a look at the central portion of the expression from Eddington while remembering that constants make no contribution to thermodynamic character. We are left with three terms that contribute: the mass of the star cubed, the mass of the sun squared, and the radius of the star squared. In terms of thermodynamic character, this simplifies to mass over radius squared. But mass is an extensive property, a homogeneous function of degree 1, while radius is non-extensive, a homogeneous function of degree 1/3. So we have a homogeneous function of degree 1 divided by a homogeneous function of degree 2/3 because radius is being squared. This is not intensive because the numerator and the denominator are not homogeneous functions of the same degree. So Eddington's solution is thermodynamically forbidden, as temperature on the right must always be equated to an expression which simplifies to an intensive thermodynamic character. Now let us just look at Eddington's equation a little more. Immediately we have a problem when we consider that beta and kappa can never be properly evaluated. Eddington actually has no idea if a star even radiates internally. Furthermore, gas pressure can only exist when a real surface is present to generate the pressure, and no such surface exists inside gaseous stars. So his term beta provides absolute flexibility because he has no idea either of gas pressure or of radiation pressure inside a star. The same is true for his insistence that he has an understanding of the opacity within Capella or the opacity within other stars. Again, his kappa gives him absolute flexibility. Eddington himself seems to understand that he might have made a serious error in deriving his expression, although no one before Crothers and I previously questioned its thermodynamic character. Here is a quotation from Eddington. "We must conclude either that we have been misled altogether in the theory of the mass-luminosity relation, or that in dense star like the sun, the material behaves as a perfect gas." Yes, he had been misled, but what is worse is that Eddington ultimately misled several generations of astronomers. The stars are simply not ideal gases. Gases can never gravitationally collapse, as we saw in this video. As a result, Eddington has no means of even building his stars. What is worse is that he now advocates for an object which could not even cool. Here is a quote: "I do not see how a star which has once got into this compressed condition is ever going to get out of it. The star will need energy in order to cool. Imagine a body continually losing heat but with insufficient energy to grow cold. Now, this has very far-reaching consequences in astrophysics because the collapse of an ideal gas has led to a myriad of faulty conclusions relative to the formation of ultra-dense objects, beginning with white dwarfs and ending with the black hole. Now, let us return to Stefan's law. One can see that luminosity for a black body is only determined by two things: the radius of the star and the temperature, the emissivity being assumed to be 1 in that case. So if a star is assumed to behave as a black body, then when the temperature is known and the luminosity is low, the only solution for the astronomers was to lower the radius. That is because they erroneously assumed that all stars could have an emissivity of 1. Of course, that is what Eddington wanted in his mathematics, since all gaseous stars, in his opinion, could be treated as black bodies, and his mathematics offered no alternative. Next, have a look at this image of Sirius A and Sirius B obtained by the Hubble telescope. Sirius A is a main sequence star, whereas Sirius B, the tiny dot on the image, is a white dwarf. It turns out that the luminosity of Sirius B is only 1/10,000th of the luminosity of Sirius A. We can get these two expressions with subscripts 1 and 2 describing each star. Now let us take the ratio of the two expressions. Let us assume that both stars have the same temperature and simplify, giving us this equation. Now let us assume that the first star has a luminosity which is only 1/10,000th of the luminosity of the second star, namely L1 is equal to 0.0001 L2. Now we have this expression. It is clear that if emissivity is forced to equal 1, then the solution is that R1 must be equal to 0.01 R2. The luminosity of the dwarf is then accounted for entirely by lowering the radius of the star and making it extra dense. Eddington does the calculation using known masses and luminosities for both stars. He ends up making the following statement. Apparently then, we have a star of mass about equal to the Sun and of radius much less than Uranus. The calculated density is 61,000 grams per cubic centimeter, just about a ton per cubic inch. With that statement, white dwarfs became incredibly dense. In Eddington's case, if the star's temperature were about equal, and both stars are assumed to be black bodies, then the only thing that could change was the radius. Eddington assumed that the emissivities of all stars could be set to 1, but he had no basis for doing so. He had no idea about the real emissivity of the white dwarf, and he never considered that lattice structure could play a part. But in the end, it is all about lattice structure. Consider this next image taken in X-ray of Sirius A and Sirius B. Now Sirius B is the brighter of the two, and the contribution from Sirius A is thought to be UV contamination, not X-ray. So what is happening now? One can see that Eddington's simple analysis of luminosity was not correct. He never imagined that Sirius B could be a powerful emitter in the X-ray, and he never included that in his analysis. He never considered that white dwarfs could not be treated as black bodies. If all stars are not gases but rather comprised of condensed matter, then everything changes. The main sequence stars have a real lattice, which was inferred to be hexagonal planar, as we discussed in this video. That was the lattice of graphite and soot, the best naturally occurring black bodies on Earth. So it makes sense for stars on the main sequence to have an emissivity of 1. This is observationally known to be true for the Sun at least. Now let us assume that the emissivity of white dwarfs is not equal to 1, but rather is much lower, precisely because the white dwarf does not possess a hexagonal planar photospheric lattice. In the white dwarf, what if the photospheric lattice has been transformed from hexagonal planar to something like a diamond lattice? In this case, the emissivity, much like the emissivity of diamond, would be very low. In a simplified analysis, one could just lower the emissivity to 0.0001 and maintain the radius and temperatures as about the same for Sirius A. We are looking at a very different emission, and Sirius B might be telling us not to treat it so readily as a black body. As a result of all this, the white dwarfs would not be the super dense objects Eddington claimed. He saw the white dwarf as providing confirmation that stars were made of super-perfect gases because he had calculated incredible densities in the white dwarf. In order to do that, he would insist that he could keep an emissivity of 1. To justify his conclusion, Eddington would invoke general relativity and argue that gravitational redshifts existed in the white dwarf. This would bolster his claims relative to density. We will go over gravitational redshift arguments and more in upcoming videos. For now, the key lesson is as follows. Stars have a real lattice, and the lattice of the white dwarf is likely to be vastly different than that possessed by the main sequence of the stars. A diamond-like lattice is a suitable choice given the lowered emissivity anticipated in this case. In the end, it is all about the Sun. The Sun has a real surface which emits a thermal spectrum. As a result, it must have a real lattice. The same must be said for other star types, including those on the main sequence and the white dwarf. This results in a terrible blow to astrophysics, which extends all the way to the impossibility that black holes exist. Once again, the stars can never gravitationally collapse. If you enjoyed the video today, promote the channel. Mention the videos to your friends and to your local astronomy club. Support me with a like and subscribe for more videos as we look more closely at the Sun, the stars, and beyond. Comments are always welcome down below, and I'll see you soon on the next video.